ATP, short for adenosine triphosphate, is the molecule responsible for cellular respiration. On a fundamental level, this molecule is important to everybody since it sustains life. However, for me, the importance stretches a little bit further than that. I'm particularly interested in evolutionary biology. Now, ATP is used across all life forms, which means it was used by the last universal common ancestor. Looking further into a process is important because if it's used by all life forms, then it must be efficient or very, very important. This is the structure of ATP. It consists of 2 adenine rings, a ribose sugar, and a phosphate tail. Adenine is a purine nucleotide, and ribose is a 5-carbon or pentose sugar. In terms of ATP, the function of these components is primarily structural in that the combination of a nitrogenous base, a pentose sugar, and a phosphate group defines this molecule as a nucleotide. The combination of adenine and a ribose sugar forms the compound adenosine. The main functional component of ATP is the phosphate tail, here. The structure of this tail consists of 3 phosphates combined with phosphoanhydride bonds. It is a common misconception that these bonds themselves are high-energy bonds, when in fact these bonds don't have any unusual properties, and it's actually ATP itself that's a high-energy molecule. However, these bonds are unstable, which allows a hydrolysis reaction to occur more easily than if they were not. ATP hydrolysis is quite simply when ATP combines with water. This produces ADP, adenosine diphosphate, H+, and 1 inorganic phosphate. In order to fully explain why ATP is a high-energy molecule, I must first explain the concepts of Gibbs free energy. This is an equation which calculates the total amount of energy available to a system. This is the equation. What this means simplistically is that the free energy is equal to the change in potential energy, or H, minus the temperature, T, multiplied by the amount of unavailable energy, S. If the result of this equation is exergonic, or energy releasing, the delta G value will be negative. So, quite simply, ATP is a high-energy compound because its hydrolysis, that is, when ATP reacts with water, releases a relatively large amount of free energy. The delta G is equal to negative 7.3 kilocalories per mole. The hydrolysis behaves this way because the reactants have more free energy than the products. This means that the overall delta G of the system is exergonic, or energy releasing. All of these reactions occur because of the structure of the phosphate tail. This has been Rebecca Bennett with the structure and function of ATP.